What is a reference mismatch?
When operating under normal conditions, systems equipped with internal, oven-controlled internal oscillators provide highly stable and synchronized reference outputs for both black and burst, tri-level sync, digital audio, and precision time protocol. This stability is achieved by locking each oscillator to a common global navigation satellite system reference, ensuring phase alignment across all timing domains. In the event that the GNSS reference is lost, each device transitions into holdover mode, relying solely on its internal oscillator to maintain timing stability. Although these oscillators exhibit excellent short-term frequency accuracy, they are not phase aligned with each other. As a result, while each reference continues to operate independently with minimal drift, the overall system loses synchronization between black and burst, digital audio, and PTP. This mismatch can manifest as frame sync errors, video phase offset, or lip sync discrepancies, particularly in hybrid SDI and IP environments where precision timing correlation is critical. The simplest way to ensure that your NTP, black and burst, tri-level sync, digital audio, AES, EBU, and PTP remain synchronized is by having all reference sources generated from the same oscillator in your sync pulse generator, and that unit is locked to a GPS reference. That way, if the signal pulse generator loses its GPS reference, both NTP, black and burst, tri-level sync, digital audio, AES, EBU, and PTP reference will use the sync pulse generator's oven-controlled internal oscillator and go into stay in sync mode. And when the GPS reference returns, a slow lock function is available to eliminate the shock that occurs when the gen lock is performed again based on stay in sync. This makes it possible to construct an extremely reliable synchronization system.
In larger systems that employ redundant LT4670 units in combination with an LT4448 Emergency Changeover Unit, additional failure scenarios can arise. These can introduce conditions where the black and burst, tri-level sync, and PTP reference sources end up coming from different LT4670s and causing reference signals to drift out of alignment, resulting in a reference mismatch. Test number 6. Overcoming a reference mismatch with black and burst stroke tri-level sync or SDI failover. When the primary LT4670 experience a black and burst, tri-level sync or SDI reference output failure, the LT4448 Emergency Changeover Unit detects the fault and automatically switches to the backup LT4670. However, because the LT4448 Changeover Unit is not part of the best master clock algorithm, the primary LT4670 continues to act as the PTP Grandmaster, even though its baseband references have failed. To ensure that the black and burst, tri-level sync, and PTP continue to come from the same LT4670, we need to link them together. And a new cable has been introduced, the LC-2185, which links the LT4670s and the LT4448, so that should a change in the status of black and burst or PTP occur, it is then possible to trigger a failover so that both reference sources continue to come from the same LT4670. Along with the new LC-2185 interconnecting cable, software version 3.0 for the LT4670 add the ability in PTP setup to link the best master clock algorithm to the emergency changeover unit therefore being able to force a failover on PTP should an error occur on a black and burst tri-level sync or SDI video output. So let's take a look at this in operation. As you can see, my Grandmaster ID is the primary LT4670 and it's displayed on the LV5600W. I'm now going to go into the PTP settings and adjust the best master clock algorithm so that it is linked to the emergency changeover unit. So now, should a failure occur on any of my traditional reference sources, it's going to impact the best master clock algorithm. So let's go across now and force a failure on the primary LT4670. And I'm going to do this by selecting the black output, and I'm going to switch black 1 off. And as you can see, the emergency changeover has switched from the primary to the backup, and also priority 1 has changed, in this case to 0, which means the best master clock algorithm has now selected the backup LT4670 as the Grandmaster, and this is reflected on the LV5600W. All this has happened automatically and seamlessly, and there's been no interruption or quality of service issues with the playout, as can be seen from the picture in the bottom right hand corner of the LV5600 display. So let's now take a look at how we restore the primary LT4670 to the Grandmaster status. And to start off with, we're going to go in and we're going to carry out maintenance on the primary. So remember, the black output was switched off. I'm now switching that back on. So that's carried out the necessary maintenance, but as you'll notice, the Grandmaster hasn't changed yet. So we go into PTP, and what we do is we reset the changeover unit, and you'll notice this now has reset the LT4448, so we're now back to black and burst coming from the primary, and then we need to reset the priority 1 value, and this will return it back to 10, and then the best master clock algorithm will take over and it will restore the primary LT4670 as the Grandmaster, and the backup will become passive again.